Hello friends. So today we are going to discuss UART in LPC1768. Basically the UART in LPC1768 contains four UARTs: UART 0, UART 1, UART 2, UART 3, which is available on chip of LPC1768 MCU. So basically you know that UART is used for serial communication, which is universal asynchronous receiver transmitter. The data packet here in LPC1768 contains for UART 5 to 8 data bits, 5 to 8 data bits you see here, and one start bit, one or two stop bit, and a parity bit. Parity bit is optional. So pin associated with the UARTs are total 8 pins are associated with the UART. So 2 for each UART. Here pin number 0.02 and 0.03 is associated for UART 0. You can see, which is function 2 for pin 0.02 and pin 0.03, which is TXDO is for transmission and RXDO for the reception, as you know in the UART, right? The pin 2.0 and 2.1 are allocated to UART 1, TXD1 and RXD1 respectively. Similarly, pin 0.10 and 0.11 is associated to UART 2, which is TXDO and RXDO respectively. Like that, TXD3 and RXD3 for UART 3 is available on pin 0.02 and 0.1. Okay, then you see the architecture for UART in LPC 1768. So basically here 3 pins are there for each UART. Okay, the 2 pin are, as you know, which is a receiver TXD and a transmitter, and one is enable pin. Okay, UART enable pin, right? Okay, so here you can see very a simple architecture. So basically in the transmission block, it contains a transmitter holding register, transmitter FIFO, and transmitter shift register with a transmitter DMA interface. Like that, at the receiver block as well contain a receiver buffer register, receiver FIFO, receiver shift register with a receiver DMA interface. Like that for the OA enable. So several blocks are available, that is interrupt controller status, FIFO controller and status, line controller and status. Like that we have IRDA and auto baud rate to generate the auto. So here generate the baud rate. So here there is a block for baud rate generator as well. So you can see the block where we are applying a peak clock directly and a fractional rate divider and main divider using DLM and DLL register. We can get a clock for UART. Okay, then we have several register associated for LPC 1768 UARTs, right? Those registers we are going to see. So first one is FCR, which is FIFO control register. So in that, bit 0 is a FIFO enable, bit 1 is a RX FIFO reset, bit 2 is a TX FIFO reset, and these are the 3 bits. Bit 0, bit 1, bit 2 are very important bits where we are enabling receiver FIFO, transmitter FIFO, and FIFO enable, right? So description you can read there. So when 0 FIFO are disabled, when 1 both RX and TX FIFO are enabled. For RX FIFO reset, when 1 RX FIFO E will be cleared and reset, like that same way in the TX FIFO. Then bit 3 is for DMA mode controller. Then bits 7 to 6 used for RX trigger level. Like that we have a LCR, line control register, which is which is used for line controlling operation, which determines the data format used in the transmission. Bits 1 to 0 means from 0 to 1 decides word length select. So you can see that when 00, when these bits are 00, 5-bit character length means the data length will be 5-bit. Similarly for 01 it will be 6-bit, for 10 it will be 7-bit, and for 11 it will be 8-bit, right? For 8-bit data transmission you must keep this word length as a 11. Bit 2 is a stop bit select. So as we see that stop bit either a 1 or 2-bit. For 0 it will be 1 stop bit, for 1 it will be 2 stop bit. So bit 3 is parity enable. When 0 parity generator and checking is disabled, and when 1 it is a enable. So bit 4 to 5 used for parity select. So here we have 4 different parity types. You can select here 00 for odd parity, 01 for even parity, 10 for force 1 stick parity, and 11 for force 0 stick parity. Then we have brake control, bit 6, and bit 7 we are using device over latch access bit. When this bit, that is bit 7, is a 0, disable the access to the divisor latch, and 1 to enable it. It is a very important bit where it enables the divisor latches for UART clock, right? When 0 it will be disabled, right? So then we have a LSR register, which is we called a line status register. It provides the status for RX and TX blocks. So you can see bit 0 is a RDR bit. When 0 RBR is a empty. When 1 RBR contain a valid data. RBR in the sense which is the register holds a received data, right? Then overrun is a bit. When overrun is condition occurs, it has a new character assembled, but the RBR FIFO is a full. In this case the RBR FIFO will not be overwritten, and the character in the RSR will be lost when one overrun is occurred. Then we have bit 2, so which is a parity error. When one parity error has occurred, otherwise it will not. Then bit 3 is for framing error, like that. Bit 4 is break interrupt. When one break interrupt has occurred, when we use UART interrupt in UART, at that time these are very useful bits. So bit 5 is a THRE bit, which is transmit holding register empty. So this is a very important bit. When 0, the THR, the register which contains the character while transmitting, right, which will be valid, which will be contains a valid data when this bit is 0. When this bit is 1, the THR is empty, right? So transmit empty tempt, this bit which is sixth bit. When this bit is 0, then THR and our TSR contains a valid data. When 1, both are empty. Like that we have error in RX FIFO. When 0, RBR contained no RX error, right? When 1, it contains at least one error. Then we have a register TER, which is transmit enable register, used to enable the UART transmission. Then we have RBR, which is a receiver buffer register. Then THR, which is a transmit holding register. Then we have a two important register, which is a divisor register. You can see here DLL and DLM, which is a divisor latch register, right, which is utilized to divide the clock, right, which we are going to discuss while we generating a baud rate later. Okay, like that we have a FDR register which contains, right, pre-scalar divisor value, which we called a DIV ADD val, means divide add value, which is pre-scalar divisor value, right. FDR 0 to 3 bit contains this value. Like that we have pre-scalar multiplier value, which is MUL VAL. Bit 4 to 7 of FDR contains this value. This value also used to divide the clock. While discussing the baud rate, we'll see this. Let's see one example program here. So initialization of UART, and we are going to write a program for UART 0. So before going to write a program, basically what we need to do here is to generate a baud rate. To generate a baud rate for UART, we need to use this formula, right, where the formula tells us that UART baud rate is equal to MUL value divided by divide add value plus MUL value into P clock divided by 16 into 256 into DLM plus DLL, right. So basically to generate or to calculate the baud rate, you need to select MUL value, right, which is pre-scalar multiplier between 1 to 15 and pre-scalar divisor value is between 0 to 14, and always consider pre-scalar divisor value is less than pre-scalar multiplier value. Let's now write a program for assuming P clock 25 megahertz for the baud rate 1,15,200 for 8-bit data with one stop bit, and there is no parity bit, right. Okay, so in order to generate a baud rate 1,15,200, let's we assume that pre-scalar multiple value is a 15, pre-scalar divisor value is a 2, and rearrange the formula given in previous slide, which is baud rate formula. I rearranged like this, right, which I kept 256 into DLM plus DLL is equal to MUL value into P clock divided by whole under bracket DUAD value plus MUL value into 16 into baud rate. So here in this baud rate is given, MUL value and prescaler divisor value, multiplier value, both we considered. Baud rate we know, peak clock we know, and we need to calculate here DLL and DLM. Okay, the value for DLL, DLM. So put this value, right? So here we put the values and we calculated. Finally we got that 256 into, you see here, 256 into DLM plus DLL is equal to 12. So what you do here, after getting this, right, you just divide this 12 by 256, divide this 12 by 256, and whatever the quotient you will get is a DLM, and whatever the remainder you will get is a DLL. So here the quotient which you get when you divide 12 by 256 is 0, which is DLM, and the remainder which you will get is 12, which is DLL. Okay, so therefore DLL is 12, DLM is 0. So now what you are going to do is you need to write a program, right? So we'll start with the program for UART transmission. In that, first we will go for main function. Okay, in the main function, let's we see how we are writing a transmission using UART, right, in LPC1768. So here in the main program, you see this in the main program, we are going to send a message, say hello, right, through the UART, right? So here we select one variable as a count for sending each character in a hello string. Then we are going to call UART0 initialization function. So let's we see what is this UART0 initialization function, okay, which is we defined in the program, right, which is we defined in the program. Okay, so in the UART initialization, right, so the first thing what we are doing here is we are selecting the pin 0.2 and 0.3 for UART0, which is TXD and RXD pin. So to select, we are using a 0 pin select register, so whose 4th and 5th bit is associated with the pin 0.2, and it is we know that it is a first function, so we are setting 4th and 5th bit of pin select 0 register as 01, and bit 6 and 7 of pin select 0 register is associated with pin 0.3, right, and this is also a second function, so therefore bit 6 and 7 we are writing the value 0 and 1, 0, 1. Okay, then we are assigning the LCR, as we know that LCR, as we seen the LCR register here, Okay, LCR register, in that only two things we are going to consider here. Other thing we are not bothering about. One is the word length. Word length is, as we know, as we already discussed, that when this bit is 1 1, it is 8 bit. For 0 0, it is a 5 bit. Like so here we are writing a program for 8 bit, so therefore this word length will be 1 1. And the DLAB, divisor latch enable bit. DLAB is divisor latch enable bit. Whenever you are putting the value, divisor value, in the DLL, DLM and MUL value and prescaler divisor value, div add value, you need to enable this bit, right? After that you need to disable this bit. So here parity select, parity enable, these are all are things we are not using because we are not adding a parity here, right? So therefore these two things are very important in LCR. So therefore here in the LCR, right, here we are selecting LCR as a 0x83. 0x83 means hexadecimal 83. You know 83 means the last two bits are 1 1, which says the 8-bit transmission, and the 7th bit is 1, which is a DLAB bit. We are enabling it. Okay, so then you see FCR, then you see the FCR bit. In the FCR bit, 3 bits we are considering. The last 3 bits, which is reset, which is a FIFO enable, right? Resetting a RX and resetting a TX FIFO, right? So therefore we are loading 07 to the bit. As we know that next value which we are loading in DLM, which we calculated, DLM is 0, using LPC UART 0, DLM equal to 0. So then we have a DLL value loading here, which is a 12. Then we are loading a prescaler multiple value, prescaler divisor value, which is 15 and 2 into FDR register as 0xF2 in terms of hex, right? After loading this divisor value, as I already told that in the LCR, the 7th bit, which is the DLAB, must enable while loading this value. After loading this value, that DLAB must be disabled. So therefore once again we are loading LCR here. Only we are making the word length bit as a 1 1, and 7th bit we are making 0, which is a DLAB. We are going to disable the DLAB here, right? This is a very important thing while you are writing the UART program. So once you return this initialization, if your initialization is a perfect, then it is very easy to write the remaining program in the UART. So once you initialize here, you see in the program after initialization, right, we are writing continuous loop here because we are sending hello continuously, right? And we are waiting till null value is to be appear, and keeps on we keeps on sending the character starting from H to O, right, with a count value to be incremented, right? Okay, so very simple function. You know how in embedded C write the function. We are just calling the UART write function here by sending each character to transmit. So let's we see this how the UART write function will work. Okay, so here we have UART write function. You can see in the UART write function, so whatever the character received, which is we are taking into tx data variable, right? So before we are loading this tx data variable into the thr register, which is actually the register where we are loading our data while transmitting. So before loading, we need to wait the THRE bit to set. Now, THRE bit to set, right? So here as the THRE bit, which is in a LSR register, which is a 5th bit, says that whether the THR is empty or not. So if the THR is not empty, or you can say it is already transmitting some value, it is not empty, already busy in transmitting some value, at that time you should not load this txd value into the THR, right? Till you have to wait till THR become empty. So here we are checking, while checking that the 5th bit of LSR is 1 or not. If it is not 1, if it is 0, means still THR is not empty. If it become 1, right? If it is become 1, at that time we can say that the THR is get empty. And you are come out from the while loop. Okay, you come out from the while loop, and then you need to load here this data into the THR, right? So that the transmission will continue, right? Okay, this is how the each character will be get transmitted. So here in the program, right, we also sending 0x 0d and 0x 0a for line feeder and to take a cursor into the next line. Okay, so this is how the UART transmission will occur. So if you see the UART receiver program, so it is same initialization we are going to do here. The only thing is here we are going to receive the character. So here I written very simple program for reception. So you can see I take here a string, a blank memory location, so that to receive, so that the received data is to be stored here. So normally same way I here in this program initialization is going on, same 8307 for FCR and DLL and DLM, the same value it is loaded. Okay, so after that, till we get a line feeder character, we are receiving all the character hello, right, which is to be transmitted, right? The character which is read is storing in a string memory, which is RX message, each character while it is receiving, right? So you just see the how we write a function for reading a character. So which is UART 0 read return. Here it is a function. You can see the function here. So here here also we are waiting for the RDR bit to be set, right? RDR bit to be set, which is in LSR, right? So RDR bit tells that the received character is a full, right? Received character is a full, so that you can get it the character from RBR while received, right? When RDR bit is set, it says that the received FIFO means received character which is in RBR is received and you can take it, right? So when it is 0, it says that still RBR is empty, it is not received anything, just you need to wait it. So therefore we are waiting here for RDR bit in LSR till it become 1. When it will become 1, the RBR is loaded in, the RBR is loaded with a received character, then you can take it, and we are sending this, returning this value back, right? And which is loaded here, you can see in the CH. The CH is further loaded into the string RX message, right? So when each character is as goes on received, right, it will be stored into the location RX message, right? This is a simple receiver transmitter program in UART. Okay, so here we'll stop and we will see the next program in the next session. Till then, take care, bye.